So, well, I know we are having unusual breaks today because it started a bit late and the logistics took some time. So next week I'll try to divide the class more equally. Okay, so for now, let's continue. So before the break, we mostly discuss the motivation for machine learning, right? Like so, I told you, well, I started by telling you that designing systems that can learn and think is really hard, right? Like we have made a lot of progress in the last 75 years or so. And let's get started. So like maybe in a few weeks, you might be able to design simple enough machine learning systems that they do reasonably complex tasks. Okay, so that's the goal for the first few weeks. Okay, so we'll start with the introduction. Like so, well, of course, like when you start any topic, like the most obvious question is like, what is this topic, right? So what is machine learning? I think I gave a definition for this in one of my slides, like which is basically to develop algorithms that will go figure out the algorithm to solve a task by just looking at examples, right? So that's one way to look at what is machine learning. Like so there is this another classical definition given by Tom Mitchell, like so one of pioneers in the field. Like so his definition is machine learning is basically a study of algorithms, okay, that improve their performance. It's called the performance VP at some task T, okay, with some experience. Okay, so according to Tom, there are three main things that you could think about when you are thinking about machine learning, which are the performance. Well, I think the most probably the first thing is task, but then like the system should be able to learn this task from some experience. And the most important thing is you should have some performance metric to figure out whether the system has learned the task or not. Okay, because we don't know the actual algorithm, we are going to rely mostly on the performance metric. Okay, so I'm going to come up with a metric which says, okay, yes, the system has learned this task, right? It could be the accuracy in prediction. Let's take the cat versus tiger example, right? Like so the performance metric could be accuracy, like how accurate. If I give 100 examples, what fraction of these examples my system is correctly identifying a cat, right? So that could be my performance metric. So I have some performance metric, and I want the system to improve on this performance metric by just looking at a bunch of examples. Is that clear? Questions? A really simple definition, but it captures the essence of the task. Okay, so let's look at some examples. So the most classical example that people talk about in any AI class is, I think, spam classification, right? So if you're using Gmail, Gmail has its like default spam classifier, which classifies some emails as spam and put it in your spam folder. By the way, even with all the recent advances in AI, our spam classifiers are still making mistakes. Okay, so you should go check your spam box once in a while because you'll be surprised there's an important email like classified as spam. The models still make mistakes. So the task here is spam classification, and the performance metric is accuracy. How accurate is my classifier? We clearly don't have systems that can have 100% accuracy. And the experience for the system is going to be basically a set of example emails. Okay. And I'm going to label these emails as spam or not spam. I'm going to collect a bunch of examples emails and say, oh, these are spams, these are not spams. And I'm going to train a system on these examples to get better at classifying a new email as spam or not. Is that clear? Okay, so let's look at a few more examples. The second example I want to give is another typical example, like or one of the earliest applications of ML or an AI, which is credit card fraudulent transaction detection. Okay, well, if you use TD like me, you would often get a message from TD saying, oh, this $1,000 transaction that you're doing looks suspicious. I'm going to block your card. Like, confirm by saying yes, like if this is something that you made, right? Like, so all the banks have this, like, so where they have a machine learning system which detects whether a particular transaction is fraudulent or not. And the moment it thinks it is fraudulent, it either blocks the system or asks you to verify, take some action, right? So in this case, the performance is going to be, again, accuracy. Like, we want systems which are really accurate in predicting whether something is spam, like a fraudulent transaction or not. And the experience here is going to be a set of historical transactions. Okay. And I'm going to mark these transactions as legitimate or fraud. Let's say somebody's credit card got stolen. They report that, oh, my card was stolen, right? And there were a bunch of transactions. We're going to label those transactions as fraudulent transactions. Okay. And it is very complex, right? Like, so, like, it might be just $100 transaction, but the context matters. Like, so it's a fraudulent transaction because somebody stole it and like used it for a particular period of time, right? Like, so the context matters here a lot. It's not an easy problem, but we do have a lot of machine learning systems deployed by banks, which is doing this task. Okay. Now let's look at slightly different kind of task. Like, the third task I want to talk about is basically playing chess. I want to train an agent that plays chess. Okay. So the performance measure here is going to be number of games won. I'm going to let this agent play against humans, like, let's say 100 times, and like, how many times did it win against the human, right? Like, that's my performance measure. And the experience here is going to be set of game trajectories, okay, from expert players. So there are a lot of these public databases of chess games, tournaments that happened in the past, like, so where you could basically get the entire list of moves for the games. Okay, so you have the entire trajectory of what happened in games, and we're going to collect this from expert players who are really good in playing the game. And we're going to use that as an example to train a machine learning system. Is that clear? Okay, so we saw a few examples of the task, right? Like, so, like, as you can see, all these tasks involves getting something as input and making some prediction, right? Like, so in this case, the case of playing chess, the prediction is going to be what move to take, right? And in the case of spam or credit card, like, the prediction is whether this is a fraudulent transaction or not, or whether this is like a spam or not, right? Like, so typically, majority of machine learning applications are like what we're going to call as prediction problem. Okay, so we are interested in making predictions. Okay, now to make predictions, your ML system, right? Like, so is going to take some input X, okay, which is basically the observation, okay, and it is going to make some prediction, okay, Y, which is the output of this system. Okay, it takes some input, which is the observation, and it makes some prediction, which is the output. And we would call this as an ML system or agent if you're coming from the AI background, or as a model, because most of these ML systems are mathematical models. Okay, so you can give whatever name you want for the system. Is that clear? Okay, so now let's look at a few prediction problems. Okay, so examples of prediction problems. So the first prediction problem is, given the size of the house, I want to predict what could be a good selling price for this house. Okay, so in this problem, the X is size of the house. Okay, somebody gives me the size of the house, and the system is going to make some prediction, which is basically the selling price. Is that clear? Like a standard example. So let's look at another example. Like, so now, let's say, given the current stock price for a company, I want to predict what would be its stock price in 10 minutes so that I can trade my stocks. Okay. So what is X here? What's X in this application? The current stock price, right? Like, so the X is basically stock price at time T, let's say. Now, what is Y? Yeah, so Y is stock price at time T plus 10. Okay. Now, let's do a few more examples. Let's say I take a picture in my phone. I want my phone to detect what object is there in the picture. Okay, so what is X and Y here? Someone else? Yeah.
This is the image and Y is the object.
In this case, X is the image, right? So typically you're going to represent your image as some sort of pixels, right? So Y is basically the name of the object. Like, so you could have a fixed category of objects. Let's say Y is going to be coming from a fixed category of objects like dog, ball, etc. That clear? Okay. So the next application, if you go deposit your checks in bank, like in the ATM machines, right? ATM machines have this reader which reads the handwritten numbers in the check, right? So basically some sort of OCR systems, like which detects what was the actual value of dollars returned and deposits in your account, right? Like, so some sort of handwritten digit prediction. Okay. So what is X and Y here? Yeah. It's the picture of the check. Like if you're doing digit by digit, like then it's some sort of like image of the handwritten digit. Yeah. So Y is going to be one of 0 to 9. Right? So let's do just one more application, which is another typical machine learning application that you use every day. At least I use every day, which is to open your iPhone to check the weather, to know whether you need to take an umbrella or not, right? Like, so I'm interested in a prediction problem where given the temperature, humidity, wind, etc., predict whether it is going to rain today or not. Okay, so what is X and Y here? So all the bunch of things that we get access to, right? Like, so which is basically the temperature, humidity, wind, etc. And what is Y? It's a 0 or 1. Like, let's say it's yes or no. Like, so whether it's going to rain or not, right? Okay, so we see a bunch of prediction problems here. And of course, you can think about many more prediction problems and many more AI applications that you are using every day in your phone, in your in the websites that you go to, etc. Right? But I think this serves the purpose. Like, so let's look at these 5 examples that we have here, right? Like, so in the first 2 examples, right? The target is some sort of real value. Like, so in the first example, the target is selling price, right? In the second example, the target is basically the stock price, which is also a real value, right? So examples 1 and 2, your Y is a real valued output, okay? On the other hand, like for the other 3 examples that you have here, right? You see your output is categorical. Right? So here it's a fixed set of objects that you could think of. Here there are only 10 possible digits, right? So here it is just 2 possible outcomes like yes or no, right? So 3, 4, and 5, right? Your Y is categorical. Is that clear? So these are actually the two kinds of prediction problems that we are going to discuss in detail in this course, okay? So when your Y is real value, okay, we're going to call these problems as regression problems, okay? And when your Y belongs to a set of categories, right? We're going to call these problems as classification problems. Is that clear? So the algorithms that we're going to develop for regression and classification, of course, they're going to share a lot of commonalities, but they have their own set of challenges as well. Okay, so because in the first kind of prediction problem, the output is infinite, right? Like, so it's from minus infinity to infinity. But in the second set of problems, like you have a fixed number of possible outcomes. So you can actually exploit this fact by developing algorithms. Is that clear? Any question? Okay, so now let's try to formalize the prediction problem a bit more, okay? So this is one way to define the problem, okay? So given some input x, okay, I want to make a good prediction of output y. Okay, we're going to call this model's prediction as y hat, just to differentiate it from the true prediction. Okay, so given some x, there is an output y that I'm looking for, and the model is going to make a prediction for this output, which is y hat. Is that clear? Now, the x, which is the observation given to the system, right, is often going to be a vector. You have a bunch of features that you care about. You put all these features into a vector. Okay, so x is a vector. Often it's a vector. It could be something more than a vector too. So which means x is represented by x1, x2 to xp. Okay, so we're going to call each of these individual things in this vector as features. Okay, there are p features. Features are individual components of the observation. Like, so for example, in the yes or no problem here, right? Like, so the features are temperature, humidity, wind, etc. So the features in this particular example is all the pixels of the image, right? Like, so, and in the first example, there's only one feature, the size of the house. Is that clear? So when you start defining the problem, you should know what are the input features. Okay, so once you have a set of input features, you make a vector out of it, and the output y, right? So y can be a scalar, could be just one output, or it could be a vector too. Is that clear? So for example, like I could have a regression problem where I'm predicting more than one thing. So can you give me an example regression problem like you're predicting more than one value? Yeah. Yeah, so coordinates of a planet. Let's say given a bunch of things, like you want to predict the coordinate of where the planet is currently, right? Like, so that's a two output regression problem, right? Like, so you could think about many other like there are many problems like where like y could be a vector. Okay, so it is true even for classification. For example, given a picture, it need not be the case that there's only one object in the picture. Like, so I take a picture of this classroom. There are many things that could be tagged, right? Like, so students or like chairs, like projector, right? Like so we could have many outputs even for classification problem. Is it clear? Okay, so just as a reminder, y is my target. Okay, what I'm doing today is also setting up the notations for the course. Okay, so like I want you to pay attention to the notations. So y is the target, and y hat is model's prediction. Is that clear? Okay, so now this is my problem. Like given some x, I want to predict y, right? How am I going to solve this problem? So as we discussed in the beginning, we're going to use some examples to learn to predict, right? So this idea of using some examples to learn an algorithm for prediction, right? Let's say this is called supervised learning. Okay, so what is supervised learning? So given a training set, let's just call this as xi, yi for I is equal to 1 to n. Okay, so again, pay attention to the notation. So we have n examples. Each example has a bunch of like x and y, right? So when I put x with I in the top, like so with brackets, it just means it's the ith example. So this is the input of the ith example and output of the ith example. Okay, so given a training set of n data points, okay, so the goal of supervised learning is to learn a prediction function, okay, function from x to y, just call it f, okay, such that given a new x, okay, f can accurately predict the corresponding y. Is that clear? So this is the crucial part. Like, so given a new x, I want this function to predict the correct y. I don't care about making correct predictions for the examples in the training set, actually. Because the examples in the training set, I already know the correct, right? So the system is going to be useful only when it is capable of predicting the correct y for completely unseen x. Is that clear? That is the goal of machine learning. Like, so we really want to design systems that predict for completely unseen examples, and we often call this capability as generalization. Okay, so generalization means making accurate predictions for totally unseen. Question? Oh yeah, well, yeah. No, we are right now. The way in which we have defined the problem right now is you have some label data set, and you're trying to learn an algorithm from it, right? Like so, how do you label it, or what happens when you don't have the labels? Something that we worry about later. Is that clear? Any other question? Okay, so generalization is a key requirement for machine learning. Okay, so if your system doesn't generalize, it is useless. So it is important that you care about making predictions for unseen examples more than caring about making predictions for whatever examples you already have in your training. Is that clear? Any questions so far? Okay, so now let's start with a simple example. Okay, so we're going to start with example application. Okay, so we're going to do housing price prediction. The very first example they gave at the beginning, right? So I'm interested in doing housing price prediction. Okay, so let's say I collected a bunch of historical sales in Montreal, for example. Okay, so I go to the public websites, collect a bunch of historical sales where I record the size of the house, and what was the selling price. Okay. Now, this is how the data looks like. So in x-axis, you have the size of the house in square feet. And in y-axis, you have the price of the house in dollars. Okay, 600. Well, I don't think you can find anything for 200K right now, but huh? Yeah. So maybe this data was from 20 years back. Okay. So, but this is one of the popular data sets that people use in classical machine learning. So this is definitely old data. Okay. So, well, to be accurate, this is not from Montreal. This is actually from Portland, Oregon. Okay. So I have a bunch of examples. I think there are 47 examples here. And this is my training set. Okay. Now, one thing to remember is we are oversimplifying the problem here. Of course, nobody predicts the highest, like the price of the house by just looking at the size, right? There are many deciding factors. Like, so what's the location? Is there a school nearby? Is there a hospital nearby? How many bedrooms? How is the neighborhood? So there are like, when was the house constructed, right? Like, so there are a lot of features that people would consider before coming up with a good price for the house. Okay. You will do that in your assignment. So you will look at like a lot of features to do the regression problem. Okay. But here, just to show you a nice visualization, we're going to pick only one feature. It's just easy for visualization when you have only one feature. Well, when you have 10 features, we cannot visualize like a 10D data point, right? Like, so for learning purposes, we're going to stick to one feature, but whatever we are learning today and next week will generalize even when you have thousands of features. Is that clear? Okay. Okay, somebody has given this data, right? Now, how do we go from this data to a model, right? So given any problem, what did I say was our goal, like in prediction? Like, so the goal is generalization, right? So which means I need some way to test whether the model is generalizing, right? So what we are going to do as a first step is to take our data and split this data into two parts. Okay, so we're going to use part of the data for training and part of the data for testing the system. So the training part are the examples I'm going to give to the system to learn from. So the testing part, I'm going to hold it separately. I will not show it to the system. The system will never see the Y in the testing part. Okay, but once the system is trained, I'm going to treat this testing part as unseen examples and test how well the model's prediction is in this unseen example. Is that clear? So we're going to use the training data set to train the model. And the testing is to check for generalization. Is that clear? Now, it is important to remember that this test set is just a proxy for real world generalization, right? Because the way in which I'm creating test set, I'm still going back to the historical records. I'm just separating some historical records and treat that as if it's my future test. But the real test happens after you deploy the system. So you train the system, you deploy it in your website. Now somebody comes up with a new house, the system is going to make predictions for a new house that is totally new, like, so we just came for sale today, right? So in some sense, this test data that you have here, this is a proxy for the true performance of the model. Is that clear? Any questions so far? Any questions? Okay, so we are still doing very simple things. Okay, so now let's go back to this example, right? Let's try to solve the problem by ourselves. Okay, so if I tell you that I have a new house and the the square feet of the house is approximately 4,250. Okay. So what would you guess as the price of this house? Yeah. Somewhere between the 2 points. Okay. By the way, I want everyone to answer at some point. Okay. So I need more answers. Okay. So the answer is somewhere between these 2 points, right? So let's say maybe here, right? Which is approximately 630K or 640K, right? How did you come up with this prediction? Okay, so you're kind of guessing the price based on some examples that exist around, right? Now, let's say I have a house which is, let's say, exactly here. Like I have another house which is exactly at 4,500. So what would you guess the price would be? Yeah, you know, we don't have enough examples. That is true. But if you want to make your best guess here, right? Yeah, but let's take this particular example. Like, so I have a house which is 4,500 square feet. So what do you think would be the price of this house? Yeah. 700,000, because we actually have another example where it is 700,000, right? Like, so now you see how we are trying to guess the price, right? Like, so we are trying to look for similar examples. Like if there's already an example that looks almost like this, so then we will go for it. If there's no example that looks almost like this, then we are looking for neighbors. And we're going to look at the price of the neighbors and make a guess, which is typically the average of the neighbors' house prices. Yeah. Yes. So why do you think we have this variability here? So why do you think we have this much variability here? Any thoughts? Yeah. Yes, because the size of the house is not the sole predictor for the price of the house. As I said in the beginning, there are many, many deciding factors for the house, right? Like so because we don't observe everything, you see this range like being spread out. Okay. The more features you add, the more structure you're going to find from this data. Is that clear? Okay, so now we have an idea of how we will solve this problem, right? So the goal for the rest of this lecture is to come up with the simplest possible mathematical model which will solve this prediction problem, okay? But let's take a 10-minute break.